Okay, so we are continuing with our discussion of trying to construct the universal covering for a topological space. At least what we are interested in are universal covers for Riemann surfaces, okay, but then this is completely of a topological nature, so it applies to any topological space. And of course I must again remind you that by any topological space we are of course going to confine ourselves to topological spaces which are Hausdorff, arcwise connected, locally arcwise connected, and locally simply connected. Okay, so let me recall quickly what I did in the previous lecture. So what had happened was, so given topological space X and a point of X, and what we wanted to construct the universal covering space for X, and so you know we have already seen that in the case of the universal covering the picture looks like this. So if P is the covering map from the universal covering space to X, then over each point small x in capital X, what you get in the fiber P inverse of X is just the fundamental group, first fundamental group of capital X based at small x, okay, and this happens for every point. So if x prime is another point, then what you get above is a copy of the fundamental group at that point x prime, and in this way the universal covering, so when I say equal to, I mean bijective as sets, okay. So there is a natural identification of P inverse X, the fiber over the point X with the fundamental group based at X, okay, and so you get this picture of the universal covering being at least as a set just gotten by putting over each point X a copy of the fundamental group based at X, okay. So this was our starting point to construct this space X sub univ. So if you recall, what we did was this is what we did. So how did we define X sub univ, at least to begin with as a set? So what we did was, well, we know what to put over X. Over X you will have to put in, you have to put pi inverse, I mean you have to put the first fundamental group based at X, okay, and what do you put at a different point x prime, okay. Above x prime what we are going to put is homotopy equivalence classes of paths alpha which start from X and end at X prime, and this so these are all paths, and the homotopy, the equivalence is with respect to fixed endpoint homotopy, okay, and so in particular if the point x prime were X, what we would put above would be homotopy equivalence, fixed endpoint homotopy equivalence of paths starting at X and ending at X, which is precisely the fundamental group at X, okay. So when x prime is equal to X, what you put above is exactly the fundamental group based at X, okay, and then I so this was how X sub univ was defined. It was defined to be paths on capital X starting at small x modulo fixed endpoint homotopy, okay. So when I say modulo fixed endpoint homotopy, I mean take equivalence classes. So this is a set of equivalence classes under fixed endpoint homotopy, and what was the map from this set to X? This was a very natural map which would send a path alpha to it would send a point which is equivalence class alpha to the endpoint, okay. So so in this case if alpha was a path ending at x prime, then this would go to x prime which is alpha of 1, okay. So this was the map from this set to x, okay, and since x is so you can see immediately that x arcwise connected would imply that this P is surjective, and we also saw last time how to convert this set into a topological space, okay. So what we did was maybe so I'll just rub this and write it properly. FEP homotopy. So topology on this set. So the topology on this set was also based on a very intuitive diagram. So you see you have this set above which is x sub u and unit, and of course that is this map P, and what you have below is your space x, and well give me a point above which is a homotopy equivalence class alpha, where alpha is therefore going to be a path from x and it is going to end at alpha of 1, okay. Now what would you expect to have as an open neighborhood of alpha, okay. You know P, finally we have to show that P is a covering map, okay. In particular it's a local homeomorphism, and you know it's an open map, and therefore you know if you are going to prescribe an open set above, its image has to be an open set below, and therefore it has to look like this, okay. And therefore what you do is you start with an open set U which is an open neighborhood of alpha of 1, and then what you do is you define a base for the topology with basic open sets of the form we call it the notation was u comma alpha. So this is this u comma alpha. This u comma alpha actually is the set of all alpha beta where you know beta is a path in u starting at alpha of 1, and of course u an open set containing alpha of 1, okay. So what are you going to what are the points in this neighborhood? Well so this is alpha of 1, this is the endpoint of alpha, I have this open set u, and then now I take another point, I take another path from alpha of 1 say beta from alpha of 1 to another point in u, okay. Then you see alpha followed by beta is certainly a path from x, okay, and that will give me a point here. So that will be this point alpha beta, okay. So nearby points here come from nearby points below, okay, and at least locally, but it's very clear that in this way nearby points go to nearby points, and that's essentially saying that P is continuous, okay. So I verified in the last lecture that sets of this form a base for the topology. That means you give the topology on this to be consisting of sets which are gotten by taking finite intersections of sets of this form and then taking arbitrary unions. So arbitrary unions are finite intersections of sets of this form, okay, and of course any open set will then be can be expressed as a union of basic open sets, okay. Any point in an open set can be surrounded by a basic open set, and that's the reason why they are called basic. Sets of this form, sets of the form alpha comma u give a base because number 1 the whole space x sub unit is actually a set of this form, namely I take the constant path at x and then I take x itself. Okay, so every point of this is just a path starting at x, which is the end point of C of x. Mind you, C of x is going to lie here. Okay, so here is x, and in the fundamental group there is a unit element. That unit element is just Cx, the constant path at x, and where will it go to? It will go to the end point of this, which is precisely x. So Cx is here. Okay, and you take Cx, it will go. You take its end point which is x, and then take the whole space x as an open set. So you get this pair, and this will include all points because x is arcwise connected. Okay, then or even by definition. Then the second thing is you take what is the property of basic open sets? You take any two basic open sets, or for that matter any finite intersection of basic open sets. If you given any point in that intersection, you should find another basic open set sitting inside that intersection. So we verified this for 2 in the following way. If gamma is a point lying in say alpha 1 comma u1 intersection alpha 2 comma u2, then gamma is contained in the set gamma comma u1 intersection u2, which is contained in this intersection, which is further contained in alpha 1 comma u1 intersection alpha 2 comma u2. Okay, so given a point in the intersection, I am able to find another basic open set which is in the intersection which contains this point. Okay, so because of this condition, you can see that all these open sets are just given by unions of basic open sets, and given any point in an open set, you can always find a basic open set surrounding that point, which is contained in your given open set. So these basic open sets are therefore the building blocks for all open sets. Okay, so this makes this into a topological space, and then this map becomes a continuous map. Okay, the map P becomes continuous, and that's also very easy to see because I'll have to just show that the inverse image of open sets are open. So if you take a point alpha in P inverse of u, where u is open in X, okay, then you know this alpha is contained in this basic open set, namely alpha comma u, which is also in P inverse u. Okay, so what I have proved is so this is the diagram. Suppose I have u and I take P inverse u and I take an alpha. Okay, then alpha is certainly contained in this pair, and that pair certainly under the map P goes into u. That means this pair will be in P inverse u. Okay, this open set defined by this data is going to be in P inverse u. So what I have proved is that every point of P inverse u is surrounded by a basic open neighborhood, okay, a basic open set which is also contained in P inverse u, and therefore P inverse u is open. Okay, so this implies P inverse u is open. Okay, so so that tells you that the map P is continuous. Okay, then the third thing that I explained was that this topology makes this with this topology the space, the topological space that you get is Hausdorff. So that's something that I again explained in the last lecture, and you see the in proving that this is Hausdorff. We use the fact that capital X is locally simply connected. Okay, so this uses the fact that capital X is locally simply connected. Okay, it uses this fact. Now we'll have to do several other things. What we need to prove, so what is left, what is it that is left out to be done? I need to show that, finally I need to show that this is the universal covering. Okay, I need to show this is the universal covering. So first of all I have to show, I have to prove certain properties of this space, this topological space. Okay, what are those properties? I need to show that this space is arcwise connected, locally arcwise connected, locally simply connected, and then finally I need to show it's also simply connected, because I told you the universal covering space is by definition a covering space for which the space above is simply connected. So I need to prove that this is arcwise connected, locally arcwise connected, locally simply connected, and simply connected. I have to prove all that. Okay, then I will have to prove that this map is a covering map. Okay, so if I had to, that means what? I will have to prove that this is a local homeomorphism. Okay, and in particular that means I will have to, it would follow that this is also an open map. Okay, so what I am going to do now is, because X already has this local properties, the properties of being locally connected, locally simply connected, the moment I prove this is a local homeomorphism, these properties will also pass on automatically to the universal covering, to this topological space. Okay, so my aim would be, first strategy would be to first somehow show that this is a local homeomorphism. Okay, then after showing that this is a local homeomorphism, then I will show that it is also a covering map. That means there is for every point below there is an admissible neighborhood. Okay, such that the inverse image breaks up into a disjoint union of open neighborhoods, each of which is homeomorphically mapped by P onto this neighborhood in X, of that point in X. Okay, so so the strategy now is to first show that the map P is an open map. So that's what I'm going to do. Look at, so you know I'm trying to prove P is a local homeomorphism, so I'm going to look at P restricted to this basic open neighborhood alpha comma u from, you know, alpha comma u to u. I'm going to look at this map. Okay, of course it's a continuous map, it's just restriction of a continuous map to an open set, so it's a continuous map. Alright, and now what is the image of this map? Okay, what is the image of this map? So you can see the image of this map, is the set of all x prime in u, or let me say x belonging to u, such that x can be connected to alpha of 1 by a path in u, right. So what is in the image of this map? If there is a point, so if there is a point which is in the image of this map, okay, then it has to be so it has to come, so if there is a point in the image of this map, okay, it has to come from a point like this, okay, and a point like this by definition involves a path which existence of a path from alpha of 1 to its endpoint. Okay, so here is my x. Oh, okay, I think my x is already fixed, I should not use this x again, fortunately. So let me use x prime, please change it to x prime. Okay, so x is confusing because x has already been fixed, the point x is fixed. Okay, so the image of this map is all those x prime which can be connected to alpha of 1 by a path in u, that is my claim. Alright, so this is quite clear, because you see, so here is my alpha, and this is alpha of 1, and this is my u. Okay, and suppose there is a point here, let me call this point as x prime, suppose this is a point x prime, and suppose it is in the image of this map P from a point above. The point above has to come from here, because I am only looking at the restriction of this map from here and I am looking at its image, okay. Then but what is a point here? A point here is of the form alpha followed by beta, it is alpha, so here alpha followed by a beta, alright. So what it means is there is some alpha followed by beta here, that will go, that is a point here in X subunit, in fact in this, you know, in this basic open neighborhood, namely alpha comma u, and you see that is going to this point here under P, okay, which by definition means that beta, if you look at the definition of this basic open neighborhood, beta should be a path in U starting at alpha of 1, okay, and the projection map takes this alpha beta to the endpoint of beta, okay. So what is going to happen is that this alpha beta, so beta is going to be a path from alpha of 1 to the endpoint of beta, which is x prime, okay. That means x prime can be connected to alpha of 1 by a path in U. Conversely, if x prime is can be connected to alpha of 1 by a path beta in U, then x prime is exactly the image of alpha beta. So the image of this map is this, which is a subset of U, this is a subset of U, okay. Now the beautiful thing is that this subset of U turns out to be an open set because X is locally arcwise connected, okay. This set, so you know, I'll give it a name, I'll just call it U sub X, U sub alpha 1, and I'll put ARC. So this notation means look at all those points in U which can be connected by an arc inside U to alpha of 1, which is a point of U, okay. So this is of course a subset of U. Now what is my claim? The claim is if so since X is locally arcwise connected, okay, U this set U arc sub alpha 1 is an open subset, it's an open subset, okay. So here again you see where this local arcwise connectedness of X is being used, okay. And why is this true? So it's quite obvious, but let me write it down. So you see, I'll have to tell you, so here is my situation, so I am on X, well here is my small x which is fixed, and then there is some alpha, this is alpha of 1, and then I have this, so this is my U, okay, and I have taken a point of U of this subset of U, so this is a point, let me call it as x prime, so let me have some more space, let me write it here, x prime, and x prime is a point in U which can be connected to alpha of 1 by an arc, okay. Now what is the condition that X is locally arcwise connected? The condition is given any point and given any open sets containing that point, you can find a smaller open set, if not that open set itself, a smaller open set which is arcwise connected, okay. Now therefore here is my point, I apply that condition to this point, so here is my point x prime and there is this open set U, so there is going to be a smaller open set, okay, which contains x prime, okay, and which is arcwise connected. So what I'll get is I'll get a V, okay. There exists an open set, an arcwise connected open set V containing x prime such that V is inside U. Okay, this is locally arcwise connected. How you give me a point and give me a neighborhood, no matter however small, I can find a smaller neighborhood surrounding that point in your given neighborhood which is arcwise connected. Okay, therefore now you see this V is arcwise connected, so every point in V can be connected to x prime, but x prime is in this, so and x prime can be connected by an arc to alpha of 1, therefore every point in V can also be connected by an arc in alpha to alpha of 1 by an arc in U. Okay, so what this means is it's obvious that V is contained in this subset. Okay, so what we have proved, you take any point of that set, I can find an open I can find an open set, okay, which contains that point and which lies inside this set, so that means the set itself is an open set. So this implies that this set is open. So the upshot of this is that P restricted to this takes this basic open set to this subset, okay, and that subset is an open set. So it's very clear that P maps this basic open set, every basic open set to an open set, so P is an open map. Okay, so this implies P is an open map. This implies P is an open map. Okay, and you know, and it also implies one more thing. It tells you that if my U to begin with was already, suppose this U was already an arcwise connected subset, okay, then P restricted to this will be surjective. Okay, if U is an arcwise connected open set containing alpha of 1, then P restricted to this basic open set alpha comma U is surjective, because since in this case U will be the same as the set of points in U which can be connected by an arc or a path from alpha of 1. Okay, so you know, these are all the steps in trying to get hold of a neighborhood of alpha which is homeomorphic to a neighborhood below. So the first thing that I get is, you take any basic open set, the image is open. Okay, and the second thing is if in particular my basic open set, the second member was arcwise connected, then this is surjective. Okay, so if U is you can see that if U is arcwise connected, then these two are the same. Okay, every point in U can be connected by an arc to alpha of 1, right. So you get surjectivity. All right, now we will have to go on to injectivity. Okay, so you know, I have this map, so I have this map is already continuous, it's open. If I choose U to be arcwise connected, it's already surjective. Okay, if I just prove it is injective, it will become a local homeomorphism, because it's an open map. The inverse map, the moment I prove it is injective, I have a set theoretic inverse, and because it is open, the set theoretic inverse will become continuous. So I have to only put more conditions on U to make it injective, okay, and then I will get a local homeomorphism. And what is that condition on U? The condition on U is you choose it further to be simply connected. Okay, so let me write that down. So let me rub this. So what we do is if u were both simply connected and arcwise connected, okay, then P restricted to this alpha comma u is injective. Okay, so let us prove this. Okay, so so the situation is as follows. So here let me draw another diagram. So this is my x, and so here is my small x. So here is alpha is the path here, and the endpoint is alpha of 1, and then I have a neighborhood u of alpha of 1 which is both simply connected and arcwise connected. Okay, I can get such a neighborhood. That is because capital X is locally arcwise connected and locally simply connected. Because capital X is locally arcwise connected and locally simply connected, I can get a neighborhood of any point of X which is both arcwise connected and simply connected. Okay, and the claim is for such a neighborhood U, for such an open set U, this pair will be homeomorphic to U under the map P. Okay, and why is that true? See, suppose you take 2 points gamma 1 and gamma 2. Okay, suppose there are 2 points and these are both in they are both in so you take gamma 1 comma gamma 2 in this neighborhood above, basic open set above, with both of them going to the same point below. Okay, so with P of gamma 1 is equal to P of gamma 2. Okay, then what does it mean? It means that both of these points will go to this point, and what is this point? This point will be just the endpoints of gamma 1, it will also be the endpoint of gamma 2. Okay, that is what this condition means. Okay, now what is the meaning of saying that gamma and gamma 2 are in this? See, it means, by this definition, it means that gamma 1 is actually alpha followed by a certain beta 1, and gamma 2 is again this alpha followed by certain beta 2, where beta 1 and beta 2 are paths from alpha of 1 to this common endpoint. Okay, so it will look like this. So here is beta 1 and here is beta 2. Okay, so alpha followed by beta 1 is the path whose homotopy class is gamma 1. Okay, so and alpha followed by beta 2 is your gamma 2. Okay, and you see the point is U is simply connected, therefore any closed loop in U can be shrunk to a point. So this beta 1 followed by beta 2 inverse, it is a closed loop in U and it is ending at alpha of 1, so I can shrink it to a point, so it is homotopic to the constant path at alpha 1. Okay, so U simply connected implies that beta 1 followed by beta 2 inverse is homotopic, fixed endpoint homotopic to the constant path at alpha 1. Okay, and of course, you know, this is the same as saying that beta 1 is fixed endpoint homotopic to beta 2, because I will have to concatenate it both sides with beta 2. Okay, and I will get this. So I hope this is clear, or if not I will write one more step. So this means that beta 1 beta 2 inverse beta 2 is homotopic to C alpha 1 beta 2, okay, and beta 2 inverse followed by beta 2 is a constant path at this point, okay. So this will be beta 1 followed by the constant path at beta 2 of 1, which is also the same as beta 1 of 1. That will be homotopic to the constant path at alpha 1 followed by beta 2 is just homotopic to beta 2, okay. So and beta 1 followed by this constant path will be just homotopic to beta 1. So essentially what I will get is beta 1 is homotopic to beta 2, okay, and if beta 1 is homotopic to beta 2, then alpha beta 1 is also homotopic to alpha beta 2. So what it will tell you is therefore that alpha beta 1 is homotopic to alpha beta 2, which means that these two homotopy classes are the same, so these 2 points have to be the same, and that will give you injectivity, okay. So let me write that down. So this implies that alpha beta 1 is homotopic to alpha beta 2, okay, and then that tells you that gamma 1 these two are the same point above, and so we have got injectivity. So what has happened is that if you were both a simply connected and arcwise connected neighborhood of this point alpha of 1, then this map is bijective, continuous and open, so it is a homeomorphism, okay. So so this implies that P restricted to alpha comma u is a homeomorphism, okay. So what this now tells you is that it tells you that P is a local homeomorphism, okay. From this you can immediately deduce that the topological space X UNIV has the properties of being locally arcwise connected and locally simply connected, okay, that you will get immediately, alright. So what would be left out is to show that it is arcwise connected, okay, and then I will have to show that P is a covering map, okay. I will have to show it is a covering map. So far we know that P is only a surjective local homeomorphism, okay. I told you the difference between this and a covering map is that it should have the unique path lifting property, okay, but we can directly see that P is a covering map, okay. So we can see that next. P is a covering map, so how does one prove that? Given alpha in this in X sub univ, take U to be a an arcwise connected and simply connected neighborhood that is open set containing alpha of 1, okay. So we take the same kind of neighborhood that we wanted to give we wanted us to give a set above which is homeomorphic to it, okay. So you take that kind of neighborhood, okay. The claim is you take just inverse image of that neighborhood, then the inverse image is going to break down into pieces, disjoint union of pieces, each of which is homeomorphically mapped by P onto this neighborhood. Therefore the alpha of 1, you see an admissible neighborhood for alpha of 1 is simply an arcwise connected simply connected neighborhood. Okay, so we know alpha p restricted to alpha comma u is a homeomorphism. We know this already. So suppose delta is a path from x to a point of u, okay, then you know this open set delta comma u, okay, this open set delta comma u is going to be contained in P inverse u, and P restricted to this delta comma u is a homeomorphism. Okay, the only thing that it uses is that u is both simply connected and arcwise connected. Alright, so it is clear that all sets of this form are going to be in the inverse image, okay, and I claim that the inverse image is exactly the union of sets of this form, okay, and I claim also that if the first members are different, then all these sets are disjoint. Okay, the union over paths delta from x to a point of u of basic open neighbourhoods of the form delta comma u, this is contained in P inverse u, okay, and the claim is that this is an equality. The claim is the above is an equality that is because of the following reason: you take an element of P inverse u, okay, then this element of P inverse u, suppose I call it as alpha, okay, then the endpoint of alpha is going to be a point of u, alright, and by what I said, this basic open neighbourhood alpha comma u is going to be inside P inverse u, okay. So for if alpha, so you know I shouldn't have fixed an alpha here, I am not fixing an alpha here, I am just saying that I mean this alpha could vary, okay. So what is really being fixed is this open set u, okay, these alpha could actually vary, alright. The only condition is that the endpoint of alpha lies inside u. So long as the endpoint of alpha lies inside u, okay, then this P restricted to this basic open set is a local is a homeomorphism, okay. So for if alpha is in P inverse u, then you know alpha is certainly a point of this basic open set alpha comma u, which is also in P inverse u. So therefore this union is P inverse u, okay. Then I will have to tell you that these are all disjoint. If I take two of these things, okay, if they intersect, I should say they are the same, okay. So if the first members are different, then I should say that they are disjoint, okay. So claim the union on the left side is a disjoint union if we consider is a disjoint union. Let me not say anything else. So if let's say some delta 1 comma u intersects delta 2 comma u, okay, suppose they intersect, all right, then I need to say that delta 1 and delta 2 are one and the same, okay, and that should be obvious if you remember the ideas following the proof of Hausdorffness, okay. So what does it mean that these two intersect? So that means there is a gamma, okay, there is a gamma in this intersection, all right. So let us draw a diagram. It means that so I have something like this. So we have gamma, a point in the intersection of these two open sets, basic open sets, and what does it mean? It means that gamma is because it is in here, it is equal to delta 1 followed by a theta 1, delta 1 followed by a beta 1, okay, let it be as it is, and then it is also equal to a delta 2 followed by a theta 2 because it is in here. So let me draw this, and of course these two being equal tells you that the endpoint of theta 1 should be equal to the endpoint of theta 2, okay, and of course the starting point of theta 1 is the endpoint of delta 1, the starting point of theta 2 is the endpoint of delta 2. So the situation is the diagram looks like this. So this is theta 1, and well, then there is one more here, which is this is theta 2. So this is theta 2, and of course theta 1 is a path in U, and theta 2 is also a path in U, okay, by the very definition of these basic open neighborhoods. And now what I will do is that I just want to say that this is a disjoint union, so I will have to say that if two members intersect then they are completely equal, okay. So I will just show that this is contained in that and that is contained in this. So what I will do, so let me start with take an element of the first member delta 1 comma u, the first basic open set, it will be of the form delta 1 beta 1, okay. So it is going to look like this, it is going to be delta 1 followed by some path beta 1, which is again a path inside U, okay, and I am going to show that this homotopy class, fixed endpoint homotopy class delta 1 beta 1 is also in this basic open neighborhood, okay. So for that what I do is I make use of the fact that U being arcwise connected, I can find a path from delta 2 of 1 to the endpoint of beta 1, and let me call that as beta 2, okay. So connect beta 1 of 1 to delta 2 of 1 by a path beta 2 in U. So of course I should say that the starting point is delta 2 of 1, okay, starting at delta 2 of 1, okay. So connected by this path, and then now notice that you see let's calculate, let's look at this, there is a closed loop here, there is a closed loop here, and that closed loop is going to be homotopic to a constant path. That is because the neighborhood U is arcwise connected and simply connected. So if I call these points, let me call this point as small y, okay, let me call this point as small y, then I have the following thing. So I take beta 1 followed by beta 2 inverse, then theta 2 and then theta 1 inverse, okay. So if I do that, okay, then I will get a then I will have to start at this point, but let me start at this point. So if I start at this point, I should take beta 2 inverse, then theta 2, theta 1 inverse, beta and beta 1. So let me look at that. The loop, so let me write that down. At y, y is just beta 1 of 1, and it's also equal to beta 2 of 1, given by, so this is my loop, so beta 2 inverse and then go by theta 2 and then go by theta 1 inverse and then go by beta 1 is homotopic to the constant path at y, since u is simply connected, okay. Now from this I'm just going to try to calculate what beta 1 is homotopic to. So you know I operate on the left by beta 2, so I will get theta 2 theta 1 inverse beta 1 is homotopic to beta 2, and then I operate by theta 2 inverse, I will get theta 1 inverse beta 1 is homotopic to theta 2 inverse beta 2, and again I will operate by theta 1 on the left, so I will get beta 1 is going to give me theta 1 theta 2 inverse beta 2. So beta 1 is homotopic to this. Now so now let me look at delta 1 beta 1. So delta 1 beta 1 will be homotopic to delta 1 followed by theta 1 theta 2 inverse beta 2, okay. But you see delta 1 theta 1 is homotopic to delta 2 theta 2, so you know I can write this as homotopic to delta 2 theta 2 inverse beta 2, and that will be homotopic because theta 2 inverse will be homotopic to a constant path. I will get delta 2 beta 2, and delta 2 beta 2 is now so what this tells you is that which in terms of fixed endpoint homotopy will mean that delta 1 beta 1 will be equal to delta 2 beta 2, but the latter, namely delta 2 beta 2, is here. So this is an element of this basic open neighbor delta 2 comma u, okay. So the moral of the story is you start with an element in delta 1 comma u, you see that it is also in delta 2 comma u, so this is a subset of that, and therefore by symmetry that is also a subset of this, okay. So they are equal, so this will imply that the two are equal. So delta 1 comma u is contained in delta 2 comma u, and by symmetry one will get well delta 1 comma u will be equal to delta 2 comma u, okay. So this completes the proof that this is a disjoint union and it is equal to P inverse u, alright, and therefore what we have proved is that if you start with an arcwise connected simply connected open set U, then that open set itself serves as an admissible neighborhood for every point that it contains, okay, and therefore P becomes a covering map, okay. So that gives you the proof of the fact that P is a covering map, alright. Yeah. So I will stop here.